last lecture we had developed the first few equations describing the first order perturbation theory. In perturbation theory, the Hamiltonian consists of two parts, H naught and H prime. For H naught, we are already aware of the solutions, and the objective is to find the effect on the energy eigenvalues by introducing the additional term H prime in the Hamiltonian. So, our Hamiltonian consists of two parts, H naught, this is known as the unperturbed Hamiltonian, and then plus H prime, which may be due to the presence of electric field or magnetic field or due to spin orbit interaction or relativity correction or anything that we can think of. The effect of this term on the eigenvalues of H naught are supposed to be small. We will illustrate that by means of an example. So, for H naught, we know the solution of the eigenvalue equation. H naught E n is equal to E n u n. For example, H naught may correspond to the linear harmonic oscillator problem or to a hydrogen like atom problem or something like that. So, for H naught we know this. So, we know this. Now, then on top of that we introduce the term H prime. Our objective is to solve this equation, H psi is equal to W psi. We introduce a parameter G, which is a parameter between 0 and 1, and we made a parametric expansion of psi. So, we said, so our objective is to find the perturbation to the nth state. So, we expand this, make a parametric expansion of psi n. So, we write psi n 0 plus g psi n 1 plus g square psi n 2 and so on. Similarly, W n is equal to W n 0 plus g times W n 1 plus g square times W n 2 and so on. We had substituted, say let us suppose this is equation 1, equation 2, equation 3 and equation 4. So, what we did was we substituted for psi n and W n in this equation. We used this and compared the equal powers of g on both sides, and we ended up with these set of equations. The first equation was H naught psi n 0 is equal to W n 0 psi n 0. This was the first equation. And then the second equation was H naught psi n 1, this is the first ordered equation, plus H prime psi n 0 is equal to W n 1 psi n 0 plus W n 0 psi n 1. Now, if you look at this equation, then you find that H naught psi n naught is an eigenfunction of the operator H naught. So, psi n naught and u n are the same. Let us first consider non-degenerate states. So, that the nth state is non-degenerate, there is only one wave function. So, then we will have, if we consider the perturbation to the nth state, then W n naught will be equal to E n, E sub n, and psi n naught will be equal to u n. because this is there is only one wave function associated with the nth state. So, we apply our analysis to non-degenerate states, non-degenerate states in which there is only one wave function. We will modify this analysis to take care of degeneracy after about during the course of this lecture. So, we have this equation that W n 0 is equal to E n and psi n 0 is equal to E n u n. Then we rewrite this, so that W n 0 is equal to E n psi n 0. Then we assume, since u's of n form a complete set of functions. So, then we had psi n 1 we assumed to be equal to A m 1 u m. We substituted here, and then H naught operating on u m will be E sub m u m. So, we substitute this in this equation. So, we get summation A m 1 E's of m u m plus H prime u n, because psi n 0 is u n, then W n 1 u n plus W n 0 is E n and psi n 1 is A m 1 u m. Okay. Then we multiplied this equation by, on the left, by u k star and integrate. So, we know that these wave functions, which are eigen functions of the operator H naught, because we have H naught u n is equal to E n u n, because this is a Hermitian operator. So, we have u k star u n d tau, which symbolically we write as k n. This is equal to the Kronecker delta symbol. So, we multiply this and integrate. So, this the first term becomes summation A m 1 E m 1 delta k m or m k plus H prime k n, where H prime k n is defined as the u k star H prime u n d tau, or, and the integration is of course over the entire space, or we can write it as k h prime n, plus using the Kronecker delta symbols we get W n 1 delta k n plus E n summation A m 1 delta k m. So, in this series only the summation is over m, all this m is the dummy variable, the summation is over m, only the m equal to k term survives, and therefore, we will have this term will be A k 1 E k 1, sorry, E k, just E k, this is just E k, plus H prime k n is equal to W n 1 delta k n plus E n A k 1. Please remember, the sum is over m and k is fixed, k is u k star, maybe u 2 star or u 3 star. So, m equal, only the m equal to k term will survive. So, this is a very important equation and we will be using this for the rest of our talk. So, we will block this and we will try to remember this. First case, you consider that k is equal to n. If k is equal to n, then this becomes 1, this delta k n becomes 1 and this becomes E k becomes E n. So, this term cancels out with this and we are left with W n 1 is equal to H prime n n. And when k is not equal to n, when k is not equal to n, then this is 0 and then we will have, if I take this to that side, so you will have E n minus E k into A k 1 is equal to H prime k n. So, this equation can be used to obtain the expression for A k 1, the coefficients in the expansion. What is A k 1? It is the coefficient of expansion of psi n 1. So, A k 1 will be equal to H prime k n divided by E n minus E k. Okay. So, we obtain the first order perturbation and that is equal to H prime n n. Now, let me give a simple example. Let me consider a simple example. Now, example is that example 1, let us consider the linear harmonic oscillator problem and let H naught is equal to p square by 2 m plus half k x square. So, this is the potential energy, this is the linear harmonic oscillator term, the potential energy corresponding to the linear harmonic oscillator, and one can write this as half m omega square x square. So, the frequency is omega is equal to under root of k, let me use the symbol mu for the mass. So, half k omega k by mu. Now, we know the eigenvalues and eigenfunctions of the operator H naught. So, H naught u n is equal to E sub n u n, where E sub n E n is equal to n plus half h cross omega, and u n are the harmonic oscillator wave functions. So, I do not read to write down. U n is equal to say n's of n h n of xi e to the power of minus half, which I am sure all of you know, and n takes the values 0, 1, 2, these are the discrete states of the linear harmonic oscillator problem. Now, we now assume that you have an additional term which is h prime, and we write h prime is equal to half b x square, and we will treat this as a perturbation. Of course, you can immediately say that we can obtain the exact solution for the problem, because k has to be replaced by k plus b. So, therefore, we know that the exact solutions. So, we know that when H is equal to H naught plus half B x square, we know that initially the energy eigenvalues were E n is equal to n plus half H cross omega, and omega was k by mu. Now, it will be k plus b by mu. So, this is my W n rigorously. I just want to tell you how to use the perturbation theory and consider this term as a perturbation and carry out a perturbation analysis. So, you have, so I know the exact results. Let me see what the perturbation theory gives us. So, we have H prime is now half B x square, and the perturbation, that is W n, of course, W n 0 is equal to n plus half H cross omega, that is under root of k by mu. This is W n 0, and W n 1 according to our perturbation theory is equal to, as we had derived earlier, this is equal to H prime n n. So, this is equal to H prime n n, or this is equal to bra n H prime get n, and therefore, if I substitute the value of H prime, so it will be half B n x square n. So, if I am able to calculate this matrix element, then my problem is solved. So, let me use operator algebra to calculate this matrix element. So, our objective is to calculate n x square ket n. If you remember, we had introduced in the linear harmonic oscillator problem two operators, A is equal to mu omega x plus I p divided by under root of 2 mu h cross omega, and then if you recall, A bar was equal to x, and x is a real operator. So, x bar is x minus I p divided by under root of 2 mu h cross omega. So, A plus A bar is equal to 2 mu omega divided by under root of 2 mu h cross omega x. This implies that x is equal to h cross by 2 mu omega A plus A bar. What is x square? X square is x times x. So, therefore, x square is equal to h cross by 2 mu omega A plus A bar times A plus A bar. So, that is A plus A bar plus A bar A plus A bar A bar. Now, as you know that A ket n, this you must remember, is equal to square root of n ket n minus 1, and A bar ket n is equal to square root of n plus 1 ket n plus 1. So, therefore, you will have So, therefore, you will have n A n. So, this will be A ket n is proportional to n minus 1, and then A ket n minus 1 will be proportional to n minus 2. So, this will be something multiplied by n minus 2, which is 0. Similarly, n a bar. So, this is n plus 1, square root of n plus 1. So, this will be square root of n plus 1, and then a bar n n plus 1 is square root of n plus 2 n plus 2. So, this is also 0, because these two numbers are differ by 2. The only non-vanishing matrix elements will be n a bar n. So, this is very easy to calculate. This will be square root of n plus 1 ket n plus 1, a ket n plus 1 is square root of n plus 1 ket n. So, this will be n. So, this is n plus 1, and then you will have n a bar a ket bar n will be square root of n and then square root of n. So, this will be n. So, if I sum them up, then we will get 2n plus 1. So, therefore, n x square n will be equal to h cross by 2 omega 2 mu omega n plus 1. And therefore, if you recollect that the matrix element, the perturbation was equal to n x square n. So, this will be the perturbation will be first order perturbation will be half b h cross half b, and therefore, this will be h cross by 2 mu omega into b half times n plus half. So, this is the first order perturbation. Now, as I told you that for this we have the exact solutions also. I think I wrote it down somewhere here. Yes, these are the exact solutions. So, I can write this down as n plus half h cross. If I take k outside, under root of k by mu, then this will be 1 plus b by k raised to the power of half. So, let me write this down. So, I have, excuse me, so I have w of n, these are the rigorously correct. So, n plus half h cross, and this is omega, and if I make a binomial expansion, and that is possible when b by k modulus is less than 1. So, I will get 1 plus half b by k plus minus 1 by 8 b square by k square plus terms proportional to b cube, then b 4, etc. And this is w n 0. So, I have w n 1, from this we say that the first term is equal to w n 0 times half b by k, and the second order perturbation can also be found out from there. Here second order perturbation will be, it will be proportional to b square. So, w n 0, which is n plus half h cross omega with a minus sign 1 by 8 b square by k square. Notice that my perturbation was h prime is equal to half bx square. The first term is proportional to b, the second term is proportional to b square. So, our parametric expansion in powers of g is therefore justified. But one must remember that this is a series which is alright only if b by k is less than 1, and in fact we cannot make this expansion if b by k is greater than 1. So, therefore, there are domains of validity of perturbation theory. It is valid for small values of b or small values of b by k. Nevertheless, this is my first order perturbation. So, this is n plus half h cross omega times half b by k, and I leave it as an exercise for you to show that this term and this term is the same. So, this is the way that we use the perturbation theory, and that is for any problem. Let us suppose h naught, this is u 0, this is u 1, this is u 2. The energy eigenvalues are E 0, E 1 and E 2, and my Hamiltonian is h naught. If now there is an additional term because of the presence of magnetic field or electric field, as we will consider later, then each energy level gets shifted, and I am assuming that this energy state is non-degenerate. So, that corresponding to particular value of energy there is only one state, and the perturbation delta E is equal to W n 1, this is equal to n h prime n, and this is also written as u n star h prime u n d tau. It is always more convenient to write it in terms of the bracket notation, because you will, if you ask me that is it a integration, one dimensional integration or two dimensional integration, the answer is it will depend on the problem. If it is a hydrogen atom problem, it is of course a 3 dimensional integration, dx dy dz or r square dr sin theta d theta d phi. If it is a harmonic oscillator problem, then it is only integration over x and so on. If it is a 2 dimensional oscillator problem, it is dx dy. So, it is more convenient to write it in this particular form. Let me consider a simpler example, example 2, an example for matrix algebra. So, we assume h naught, this is an example from matrix algebra. So, I have 1 0 0 minus 1. So, it has 2 eigenstates, ket 1 we denote by ket 1 0, and the eigenvalue is E 1 is equal to 1. This is a diagonal matrix, this is a Pauli spin matrix if you recollect, and the other eigenstate is 2, which is 0 1, and E 2 is equal to minus 1. So, I have 2 states. So, plus 1 and minus 1, plus 1 and minus 1. I denote this by ket 1 and denote this by ket 2. Now, let us suppose there is a perturbation, that I apply, and let that perturbation be denoted by h prime, and that is equal to a very simple matrix epsilon 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 epsilon. So, what is the perturbation to this? So, I can calculate delta E 1, which is equal to say the perturbation, the first order perturbation to the first state. The superscript 1 represents, this is the first order perturbation. The subscript means that it is the first state. So, this will be bra 1 H prime ket 1, and so if I do this 1 0 epsilon 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 1 0. So, if you multiply this out, you will get epsilon. So, the first order perturbation is, therefore, this is plus epsilon. So, the energy level shifts, the eigenvalue shifts by epsilon. Similarly, I can write down delta E 2, which is the perturbation to the second state, first order perturbation to the second state. So, this is 2 H prime 2, and I leave it as an exercise for you to show that that is also equal to epsilon. So, this state shifts by E, this state also shifts by epsilon. This is the perturbation. Once again, you can say, can we not solve this problem exactly? The answer is yes. So, I have H naught is equal to H naught, if you recollect, is 1 0 0 minus 1. So, my complete matrix. So, the complete matrix is H, which is equal to H naught plus H prime, H naught plus H prime. So, this will be equal to 1 plus epsilon 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 minus 1 plus epsilon. So, this is my total matrix, and the determination of the eigenvalue is very straightforward. I write down the determinant. So, this will be minus 1 plus epsilon minus lambda epsilon epsilon plus 1, here it is plus 1, and here it is minus 1 plus epsilon minus lambda. So, this gives me this times this. This is epsilon minus lambda, if I put it in bracket, plus 1. This is epsilon minus lambda minus 1. So, this becomes epsilon minus lambda whole square minus 1 minus epsilon square is equal to 0. The solution of this equation will give me the eigenvalues of the problem. So, let me write it down once again. So, I have, in order to find the values of lambda, epsilon minus lambda whole square minus 1 minus epsilon square is equal to 0. So, the first term is epsilon square, that cancels out with this. So, you have lambda square minus 2 lambda epsilon minus 1 is equal to 0. So, if the roots of this equation is lambda is minus b, that is plus 2 epsilon plus minus 4 epsilon square minus 4 AC, that is plus 4 divided by 2. So, this will be epsilon plus minus 1 plus epsilon square raised to the power of half. So, assuming epsilon to be less than 1, we can make a binomial expansion. So, we get epsilon plus minus 1 plus half epsilon square minus 1 by 8 epsilon to the power of 4 plus so on, epsilon to the power of 6. So, I get please see this, the eigenvalues as plus minus 1 plus epsilon plus minus half epsilon square minus plus 1 by 8 epsilon to the power of 4. So, please see this, that this is W n 0, the unperturbed eigenvalue in the presence of epsilon going to 0, for epsilon going to 0. The first order perturbation is the same for both states, and this is what we had obtained here also. This was 1 plus epsilon, this was 1 minus epsilon. This is the first order perturbation. This is the first order perturbation. The second order perturbation, this is W n 2. So, this is half epsilon square and minus half epsilon square. Half epsilon square for the plus 1 corresponding to the half eigenvalue minus, and then W n 3, the third order perturbation is 0, and this is the fourth order perturbation. So, this is the exact result, and we see that the first term is first order perturbation, second order perturbation, the third order perturbation is 0, this is the fourth order perturbation. Once again, this binomial expansion is only valid when epsilon is less than 1. So, therefore, the perturbation theory will not be valid when epsilon is greater than 1. So, therefore, the perturbation theory is usually valid, we say, for small perturbation. In fact, it will be a divergent series if epsilon is greater than 1. So, therefore, it does not work often when the parameter becomes large. Okay. So, I have given you one example from the harmonic oscillator problem and another example from the theory of matrices. Now, we go back to our first slide and we try to where did I put? Yes, we go back to our this slide. We said that n is equal to k, n is equal to k, then we had W n 1 is equal to H prime n n. But let us suppose I have the state is, the ground state is represented by U 0 and the first excited state is, let us suppose, two-fold degenerate. That means there are two eigenkets corresponding to that, a U 1, U 2 eigenfunctions corresponding to that. We know that if this is a degenerate state, a two-fold degenerate state, then you can have any linear combination of that to be also an eigenfunction. That is if U 1 is an eigenfunction and U 2 is an eigenfunction corresponding to a degenerate state, then U 1 plus U 2 by root 2 is also an eigenfunction. And so, therefore, the question arises, if I want to calculate H prime n n, then it is U n star H prime U n. Then for this, to calculate this, should I use U 1, should I use U 2 or some linear combination of that? So, therefore, psi n 0, we had said that H naught psi n 0 was equal to W n 0 psi n 0. Now, I can consider the perturbation to the second state. So, W n 0, I know this is equal to say E 1. So, this is E 0 and the energies are the energy is E 1. So, E 1 and E 2 are equal. So, you have H0 U1 is equal to E1 U1 and H0 U2 is also equal to E1 E2. This is the same eigenvalue. That is the concept of degeneracy. This is two linearly independent wave functions which correspond to the same energy eigenvalue. Then the question arises, will psi n naught be U1 or U2 or some linear combination of that? So, we do not know, and so therefore, let us consider twofold degeneracy and we assume that this is equal to C1 U1 plus C2 U2. We take any two sets, any two functions which are orthonormal to each other, and we write psi n0 as a linear combination of that, and our objective is to determine the values of C1 and C2. So, we once again assume that psi n0 is equal to C1 U1 plus C2 U2. Then we will have that so therefore, you will have the equation A we will write this equation. Let me go from one step behind and let me just go back to that slide. Yes, we start with this equation. So, we have H naught psi n1 plus H prime psi n0 is equal to W n1 psi n0 plus W n0 psi n1. Now, we are assuming this is E0 and this is the second state which is twofold degenerate state. So, we have H naught psi n1. So, we wrote down that H naught summation A's of M1 U M plus H prime C1 U1 plus C2 U2 is equal to W N1 C1 U1 plus C2 U2 and W N0 is E1. So, this is E1 summation A M1 U M. Now, I first multiply this by U1 star and integrate. So, H naught this I have to write again, because the first term will be summation A M1 E M U M. So, first we multiply this term becomes this term and the remaining terms remain the same. I do not want to rewrite it. I then multiply by U1 star and integrate. So, I get A 1 1 E1 because only the first term will survive plus within brackets C1 H prime 1 1 plus C2 H prime 1 2 is equal to W N1. I am multiplying by U1 star. So, this is just C1 and this will be 0, E1 star U2 will be 0 plus E1 A11. So, as you can see that this term cancels out with this term, and if I take from this on this side, we will get the equation. We will get the equation C1 H prime 1 1 minus Wn1 plus C2 H prime 1 2 is equal to 0. This is one equation. Then what we do is I multiply by U2 star and integrate. So, this will become A21, but this will be E1 because E1 is equal to E2. E1 is equal to E2. We had said that H naught U1 is equal to E1 U1 and H naught U2 is also equal to E1 U2. They correspond to the same energy eigenvalue. So, this term and this term will again cancel out, and what will be remaining is C1 H prime 2 1 plus C2 H prime 2 2 minus Wn1. This is a set of linear homogeneous equations, and for non-trivial solutions the determinant must be 0, that is H prime 1 1 minus Wn1 H prime 1 2 H prime 2 1 H prime 2 2 minus Wn1. This determinant must be equal to 0. So, that solves my problem. That solves my problem. This is I hope all of you understand that. For example, if I have an equation like this, Ax plus By is equal to 0 and Cx plus dy is equal to 0. Then the trivial solution is x is equal to 0 and y is equal to 0. That is the trivial solution. But otherwise, you will have A, B, C, D, the determinant of that will be 0, because y by A will be equal to minus A by y by x will be minus A by B is equal to minus C by D. So, AD will be equal to CB. So, this is a set of linear homogeneous equations for C1 and C2. The trivial solution corresponds to C1 is equal to 0 and C2 is equal to 0, but for non-trivial solutions you will have the determinant equal to 0. Now, this determinant, this is you will obtain a quadratic equation in Wn1, will allow us to give two roots, in general two different roots. For each root you will obtain two different values of C1 by C2, and that will give me two different eigenfunctions of the system. And therefore, the recipe is this, that if I have a two-fold degenerate state, the corresponding eigenfunctions are u1 and u2, and let us suppose this is u0, u3, u4 can be anything. The recipe is this: my perturbation is H prime, I assume psi n0 is equal to C1 u1 plus C2 u2. then I obtain these set of two equations, and from these set of two equations we obtain these secular determinant equal to 0. The solution of this equation will give me two values of Wn1, and for each value of Wn1 I will get the ratio C1 by C2. In general, if it is, let us suppose, a three-fold degenerate state or a four-fold, let us suppose it is three-fold degenerate. So, then I must write down C3 U3, and then we will have a set of three equations. Please see, C1 H prime 1 1 minus W1 plus C2 H prime 1 2 plus C3 H prime 1 3, this is equal to 0, and similarly C1 H prime 2 1 plus C2 H prime 2 2 minus W1 plus C3 H prime 2 3 equal to 0, and then C1 H prime 3 1 plus C2 H prime 3 2 plus C3 H prime 3 3 minus W1 equal to 0. This will lead to a 3 by 3 determinant for non-trivial solutions, and therefore we will get 3 roots of W1, and for each value of this we will get C1 by C2 and C1 by C3 if all three of them are different. So, that is the recipe for the degenerate state perturbation theory calculations. Let me take an example, and we will take an example from, so this is my example 3 from matrix algebra. So, let me consider H naught is equal to 1 0 0 1 1 0 0 1. Then we will have that this, as you know, has only one eigenvalue plus 1. What are the eigenfunctions? It will be, it can be either, you can choose 1 0 or 0 1, this is an unit matrix, or I can choose 1 1 under root of root 2 and 1 over root 2 1 minus 1. It does not really matter. I can choose these two as eigenkets, or these two as eigenkets. Any linear combination of these two can also be an eigenket. I can choose as 1 plus I and 1 minus I. You remember, these are the eigenfunctions of the eigenkets of the Pauli matrices. So, this is a, so the question arises, let us suppose that my H prime is once again epsilon 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 epsilon. So, let me choose these as my base kets, that is ket 1 is equal to 1 0 and ket 2 is equal to 0 1. So, therefore, H prime 1 1, I have to calculate all 4 matrix elements. H prime 1 1 will be 1 0 epsilon 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 1 0. So, this will come out to be epsilon. So, all the values, so H prime 2 2, H prime 2 1, everything. So, H prime 1 2, let us suppose H prime 1 2 is 1 0 epsilon 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 epsilon, and this is 0 1. So, this is again epsilon. So, all matrix elements are epsilon. So, the determinant, the secular determinant becomes epsilon minus W epsilon 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 minus W is equal to 0. So, you have epsilon minus W whole square is equal to epsilon square, epsilon minus w is equal to plus minus epsilon, or you have w is equal to the first order perturbation. First order perturbation will be, if I take a epsilon here, so epsilon minus plus epsilon. So, one will be 0 or 2 epsilon. These are the two perturbations. So, we will continue from this point onwards in in our next lecture. So, we end here. Thank you.